The objective of our project was to determine the forces and moments on a basketball hoop and the support it's attached to. Before we get into any of that, there's a couple assumptions we need to make this more applicable to what we're doing in class. As fun as it would be to model Shaq breaking all these backboards, that's a little too complicated and out of the scope of the class, so we're just going to assume that the system is in static equilibrium and the player's hanging off the rim. This is a sketch of the hoop and support system we analyzed dimension to NBA standards. Using a combination of free body diagrams and the three equilibrium equations, that is, the sum of forces in the x and y direction are equal to 0, and the sum of moments about any point is also equal to 0, we were able to effectively determine the forces and moments at any point A through J in the system.
First, we needed to determine the support reactions at the base of the structure. Assuming the pole supporting the backboard weighs 90 pounds, the backboard itself weighs 50 pounds, and the player weighs 180 pounds, we obtain the following equations. We also assume the weight of all other components is negligible. Solving these equations, we see that the horizontal reaction force is 0 pounds, the vertical reaction force is 320 pounds, and the moment reaction is 930 foot-pounds.
Next, we need to determine the forces supported by the individual members. We made free body diagrams for each of the members as shown. We then identified all members that have two forces acting on them and labeled their forces first. As you can see in the diagram, members AE and IJ are the only two force members. After the free body diagrams for the two force members are completed, we added those results to the remaining free body diagrams and solved for the remaining forces.
Assuming members AE and IJ are under tension, we can see that they satisfy the equilibrium equations. From the remaining three members, we can see that the member with the least amount of forces to solve for is member EGF, so we solve that first. Observing the geometry of member AE in this diagram, we can deduce that the horizontal and vertical component of the force TAE is given by the following equations. Examining member EFH, taking moments about F, which should sum to 0, we obtain a force TAE of 376.2 pounds. Resolving forces in the x and y directions, which should sum to 0, we obtain that f of x equals 293.8 pounds and f of y equals 465 pounds. Finally, examining member IBF, taking moments about B, which should sum to 0, we get a force of TIJ that equals 920 pounds. Summing forces in the x and y directions, which should also sum to 0, we get B of x equals 293.8 pounds and B of y equals 1,385 pounds.
And with that, we have successfully determined all unknown forces as shown. Writing equilibrium equations for member ABCD would be redundant. We hope you enjoyed this presentation. If you have any questions, please hesitate to ask, because we don't want to answer them. Thank you.